Dear friend, welcome to this exploration of quantum fields and the hidden structures of the universe. Tonight, we'll journey through the subtle forces that shape our reality, from the restless vacuum to the promise of new discoveries beyond the standard model. Let your mind drift through these quiet currents of nature, and allow the gentle murmur of the quantum world to carry you into a deep and peaceful sleep. Chapter 1. Introduction to Quantum Field Theory, a New Language of Reality. Quantum field theory, or QFT, is the language that modern physics uses to describe the most fundamental behaviors of our universe. It is a language that replaces the comfortable certainties of classical physics with an intricate web of fields and their fluctuations, a framework that can describe everything from the smallest particles to the largest cosmic structures. In this chapter, we will take a deep breath and step into this realm of fields to understand how they have transformed our understanding of matter and the forces that govern it. At first glance, the idea of a field might seem abstract or even intangible. Yet fields are, in many ways, more fundamental than the particles we once thought of as the building blocks of matter. In classical physics, a field is a mathematical entity that assigns a value to every point in space and time, like a temperature map that tells you how warm or cold it is in every room of a house. The electric field is perhaps the most familiar example. It tells you how an electric charge placed at any given point would feel a force, describing a gentle push or pull across space. Quantum field theory takes this idea and expands it, bringing it into the quantum world. Here, fields are not merely mathematical conveniences or abstract constructs. They are real, dynamic entities that ripple and dance across the vacuum of space, shaping the very fabric of reality. Every particle we know of, the electron, the photon, the quarks that make up protons and neutrons, is an excitation of a corresponding quantum field. Imagine for a moment a perfectly still pond. In classical physics, a stone dropped into the water would create ripples, and you would see those ripples move across the surface. In QFT, however, it is as if the entire pond is alive with invisible ripples, even when no stone has been dropped. The pond itself is the field, and particles are the ripples, temporary disturbances that travel across it. In this picture, an electron is not a tiny sphere of matter, but a localized wave in the electron field. This shift in perspective is profound. In the quantum view, there is no true emptiness, no region of space that is truly still. Even what we call the vacuum is a seething ocean of fields, each one fluctuating with a restless energy. These fluctuations are not just mathematical curiosities. They have measurable effects, as we will see in later chapters. They are the whispers of the fields that make up our reality. The development of quantum field theory was driven by the need to reconcile quantum mechanics with the demands of special relativity. Quantum mechanics had already revealed that particles behave like waves, and that their behavior is governed by probabilities rather than certainties. But in the early 20th century, physicists faced a new challenge: how to describe particles that travel close to the speed of light, and how to account for the fact that energy and matter can turn into each other in high-energy collisions. QFT emerged as the answer to this challenge. It provides a framework that naturally incorporates the principles of relativity and quantum mechanics, describing particles not as isolated objects, but as excitations in continuous fields. In this view, the interactions between particles arise from the interplay of their fields, weaving a dynamic tapestry that underlies all of nature's phenomena. One of the most striking aspects of quantum field theory is its inherent flexibility. In the world of fields, particles can be created and destroyed, as if reality itself is fluid and ever-changing. When two electrons repel each other, for instance, it is because their fields are interacting through the exchange of virtual photons, temporary disturbances in the electromagnetic field that exist for just an instant. These ephemeral exchanges are not just poetic metaphors. They are the actual mechanisms by which forces arise in the quantum world. The power of QFT lies in its ability to describe not just individual particles, but also the forces that bind them together. In the standard model of particle physics, the fundamental forces, the electromagnetic, weak and strong interactions, are all described using the language of quantum fields. Each force has its own field and its own carrier particles. The photon for electromagnetism, the W and Z bosons for the weak force, and the gluons for the strong force. The mathematical elegance of this framework is matched only by its predictive power. Quantum electrodynamics, or QED, the quantum field theory of light and matter, has been tested to extraordinary precision. It predicts the magnetic moment of the electron with an accuracy that surpasses any other scientific prediction ever made. Such success is a testament to the idea that fields, not particles, are the ultimate foundation of the physical world. Yet for all its power, quantum field theory does not offer a complete picture. Gravity, the force that shapes galaxies and bends the path of light around stars, remains outside the standard model. Attempts to create a quantum field theory of gravity to unify all forces into a single framework remain among the deepest mysteries in physics. These challenges do not diminish the triumph of QFT, but instead hint at how much more there is to learn. One of the most surprising aspects of QFT is the notion that the vacuum itself is not empty. In classical physics, a vacuum is the absence of matter and energy, a perfect void. But in QFT, the vacuum is alive with fluctuations, tiny ripples in the fields that cannot be entirely stilled. These zero-point fluctuations give rise to real, measurable effects, like the Casimir force that gently pushes metal plates together in a vacuum, or the Lamb shift in the energy levels of hydrogen atoms. This restless vacuum is a reminder that stillness is an illusion in the quantum world. Even when all seems calm, the fields are at play, weaving the very fabric of space and time. It is a humbling realization, one that challenges our classical intuitions and invites us to see the universe in a new light. To describe these fields mathematically, physicists use the language of Lagrangians and path integrals, formalisms that capture how fields evolve and interact over time. The details can be daunting, filled with intricate symbols and complex calculations. But at their heart lies a simple idea, that nature is a symphony of fields, each one contributing its unique melody to the music of the cosmos. For the physicist, QFT is not just a theory. It is a toolkit, a method of translating the strange behavior of the quantum world into concrete predictions. In particle accelerators, fields come alive in collisions that briefly reveal the universe's deepest symmetries. In the quiet of the laboratory, experiments probe the structure of fields with astonishing precision. In the glow of a neon light or the flicker of a computer screen, the whispers of these fields are present in every interaction. The success of quantum field theory is a testament to the power of human curiosity and imagination. From the first hints of quantum behavior in the early 20th century to the discovery of the Higgs boson a century later, QFT has been the guiding star of modern physics. It is a theory that is at once abstract and deeply connected to the world we see and touch. And yet, for all its precision and elegance, QFT leaves us with mysteries that stir the imagination. What lies beyond the fields we know? Are there hidden forces or particles waiting to be discovered? Could the very structure of space and time be woven from quantum fields we have yet to glimpse? These are questions that scientists and dreamers alike continue to ponder. As you let these thoughts settle and drift into the quiet of sleep, consider this, that everything around you, the air you breathe, the stars above, the thoughts in your mind, is shaped by the gentle, persistent ripples of quantum fields. In the stillness of the night, the fields remain at play, weaving the universe into existence. And though we may never fully grasp their secrets, we are forever bound to their gentle currents, carried by the invisible tides of the quantum world. Chapter 2. Fields, not particles. How fields shape everything. When you close your eyes and imagine the world around you, you might picture solid objects, a cup of coffee resting on a table, the glow of a distant star, or even your own hand held up in front of your face. For much of human history, this view of the world as made up of solid objects, particles that occupy space and have mass, has served us well. From the smallest grains of sand to the largest planets, this perspective has been a foundation of our understanding. But as we peer deeper into the heart of matter, we find that the world is not built from little marbles or rigid spheres. Instead, at the most fundamental level, reality is composed of fields. This shift from particles to fields is one of the most profound conceptual leaps in all of science. It changes not only how we describe the universe, but how we imagine the very nature of existence. A field, in the language of physics, is a physical entity that assigns a value to every point in space and time. In the simplest cases, like a temperature field, this value might just be a number, how warm or cold it is in each part of a room. But in the realm of quantum fields, these values become richer, describing not just temperatures, but complex properties like charge, spin, and momentum. The most familiar example of a field in classical physics is the electromagnetic field. Picture a magnet resting on a table, invisible lines of force extending from it like the rays of a sun. If you place a small compass nearby, it will align itself with these invisible lines, tracing the direction of the field. In the same way, charged particles like electrons and protons are constantly feeling the influence of the electromagnetic field, guided and shaped by its invisible presence. Quantum field theory takes this idea and elevates it to the deepest level of nature. In this framework, every fundamental particle we know of is not a tiny, indivisible dot, but rather a ripple, a localized disturbance within its corresponding field. The electron is a ripple in the electron field, the photon is a ripple in the electromagnetic field, and so on. The fields themselves are everywhere, even in what we would normally call empty space. To imagine this, think of the surface of a calm lake. Even on the stillest day, there are tiny ripples and swells, movements too subtle for the naked eye. In the same way, the quantum fields that fill the universe are never truly at rest. They undulate, they quiver, and in those tiny motions, particles are born. This perspective has several important implications. First, it means that what we see as particles are really just the visible excitations of something more fundamental. When you see a beam of light, you're not just seeing a stream of photons, you're seeing the electromagnetic field in motion. When you look at your own reflection, you're seeing the dance of electrons in your skin and in the mirror, ripples of quantum fields bouncing and interacting. Second, it means that the vacuum of space is not truly empty. Even when there are no particles present, the fields are still there, filling every corner of the cosmos. These fields have a kind of quiet presence, a readiness to ripple into existence if the right energy or disturbance is introduced. They are the stage on which the universe plays out its dramas, always there, even if the actors have momentarily stepped off stage. The idea of fields as the true building blocks of nature can seem abstract, but it is grounded in the most careful experiments ever performed. For example, when scientists measure the behavior of electrons in a magnetic field, or when they observe how light bends around massive objects in space, they are seeing the fingerprints of these fields. The patterns of force and energy they detect can only be explained by the presence of fields that permeate everything. In fact, one of the triumphs of quantum field theory is its ability to make sense of these patterns with astonishing accuracy. The calculations involved are not easy. They require imagining how these fields interact, how they tangle and untangle with each other in a constant ballet. But when the calculations are done, the predictions match what we see in the laboratory to a degree that is almost eerie in its precision. One of the most powerful consequences of thinking in terms of fields is that it unifies the seemingly disparate elements of matter and force. In the classical picture, you might think of particles as things that move and forces as what push them around. But in the quantum field picture, both are manifestations of the same underlying reality. Forces are simply the way that fields influence each other, while particles are the ripples that fields create. When two electrons repel each other, for example, they are not flinging tiny projectiles back and forth. Instead, their fields overlap and interact, exchanging virtual photons, brief disturbances in the electromagnetic field that carry momentum and energy between them. These virtual photons are not particles in the traditional sense. They cannot be directly observed. But their effects are real and measurable, seen in the way that electrons scatter off each other or in the patterns of light emerging from atoms. This interplay of fields goes even deeper. The strong nuclear force, which holds the nuclei of atoms together, is described by the fields of quantum chromodynamics. Here, quarks are ripples in the quark fields, and the strong force arises from the interactions of these fields through the mediation of gluons. It is a world where the concept of color charge replaces electric charge, and where the fields themselves create a binding so powerful that quarks are never seen alone. Even gravity, that most familiar and yet most mysterious of forces, can be thought of as a field in the language of general relativity, a warping of space-time itself. Physicists are still searching for a quantum field theory of gravity, but the idea remains the same, that the geometry of the universe is just another kind of field, one that shapes the motion of everything from planets to light beams. These insights reveal a universe that is far more subtle and interconnected than the old view of hard, solid particles bouncing around like billiard balls. In the quantum field view, there is no true separation between objects and their surroundings. The fields extend everywhere, weaving all of existence into a single, continuous fabric. This picture of fields shaping everything might seem remote from everyday experience, yet its implications ripple outward to touch everything we do. The light from your smartphone, the glow of the sun, the stability of the atoms in your body, all are phenomena that arise from the ceaseless motion of quantum fields. The color of the sky and the warmth of a fire, the flicker of a fluorescent bulb and the pulse of a laser, are all dances of fields responding to each other. In the laboratory, physicists can now create and manipulate these fields in ways that would have seemed like science fiction just a century ago. They can create artificial atoms out of fields of light, trap and control individual ions with fields of electric and magnetic force, and even measure the tiny fluctuations of the vacuum itself. These are not just technical achievements. They are windows into the deepest structure of the universe. Yet for all we have learned, there remains a quiet mystery at the heart of this vision. If fields are the true substance of reality, what does that say about our own place in the cosmos? We too are ripples in these fields. Our thoughts, our bodies, our histories, all composed of the same shimmering patterns of energy. The boundaries we draw between ourselves and the world around us are, in some sense, illusions. We are not separate from the quantum fields. We are expressions of them. As you drift deeper into sleep, let this thought settle into your mind, that every breath you take, every beat of your heart is carried on the invisible tides of these fields. In the stillness of the night, they remain at play, shaping the stars above and the quiet thoughts within you. And though we may never fully grasp their mystery, we are bound to them, woven into the endless, whispering song of fields that shape everything. Chapter 3. Quantum electrodynamics, light's quantum playground. Quantum electrodynamics, or QED, is a triumph of human curiosity and a testament to the power of quantum field theory. It is the quantum theory that describes how light and matter interact, weaving together the electromagnetic field and the particles that carry electric charge into a seamless, mathematically consistent framework. In this chapter, we step into the shimmering world of photons and electrons, a world of interaction so precise and subtle that it defies classical logic and reveals a new order beneath the surface of what we see. At the heart of QED lies the electromagnetic field, an ever-present backdrop that defines the behavior of electrically charged particles. In the classical view, this field acts as a medium through which electric and magnetic forces travel, a kind of invisible scaffold that supports the structure of matter. But in the quantum picture, this field becomes something far more dynamic, a stage where particles of light, the photons, constantly flicker in and out of existence, binding together the motion of charged particles in a dance that never ceases. Photons, the quanta of the electromagnetic field, are not just abstract ideas. They are the very particles of light carrying energy from distant stars to your eyes, from the warmth of the sun to the glow of a firefly. In the language of QED, these photons are excitations of the electromagnetic field, ripples of pure energy that move at the ultimate speed limit of the cosmos. They have no mass, yet they exert forces guiding the interactions of electrons and protons in atoms and shaping the chemistry of life itself. QED's power lies in how it describes these interactions. When two electrons approach each other, they do not collide like tiny billiard balls. Instead, their electromagnetic fields overlap and begin to whisper to each other, exchanging photons in a conversation that spans space and time. These photons are virtual, fleeting disturbances that exist for only the briefest moment, unobservable on their own, but essential to the structure of matter. They are the invisible messengers of the electromagnetic force, carrying momentum and energy in delicate exchanges that govern the behavior of atoms and molecules. The elegance of QED emerges from its precision. It can predict with astonishing accuracy how these interactions unfold, providing a mathematical description that matches experiment after experiment with uncanny fidelity. From the magnetic moment of the electron to the subtle shifts in the energy levels of hydrogen atoms, QED's predictions have been tested and confirmed to an extent that no other theory can rival. It is a framework so exact that it reveals not just the outlines of nature's laws, but their intricate texture. To capture these processes, QED uses the language of creation and annihilation, terms that might seem dramatic, but which capture the essence of quantum interactions. When a photon is emitted by an electron, it is created from the energy of the electromagnetic field, a new wavefront that carries information away at the speed of light. When it is absorbed, it vanishes, its energy transferred to the motion of another charged particle. In these acts of creation and annihilation, the universe maintains its balance, a quiet accounting that preserves the conservation of energy and momentum at every instant. The consequences of this framework are all around us, though we rarely stop to consider them. The light that streams through a window in the morning is not just a warm glow. It is the result of countless interactions between photons and electrons, each one a quantum event that shapes the color and intensity of what we see. The gentle push of sunlight on your skin, the sparkle of a distant star, all are woven from the threads of QED, a tapestry of light and matter that spans the universe. One of the most intriguing aspects of QED is how it describes the process of scattering, where charged particles deflect off each other or exchange energy through the mediation of photons. In the classical picture, such scattering might be pictured as particles bouncing off each other like hard spheres. But in QED, these events are more like conversations between fields. When an electron encounters another charged particle, They begin to trade virtual photons, adjusting their paths with each fleeting exchange. These interactions are so rapid and so fine that they appear smooth and continuous on our human scale. Yet each step is quantized and governed by the rules of QED. Another hallmark of QED is the phenomenon of vacuum polarization. Even the vacuum, that most seemingly empty of spaces, is alive with the activity of virtual particles. In QED, the presence of an electric charge disturbs this vacuum, drawing out pairs of virtual electrons and positrons from the fluctuations of the electromagnetic field. These pairs momentarily screen the charge, altering the field around it in a subtle but measurable way. This effect, though invisible, is real, and it has been observed in precise experiments that probe the tiny shifts in energy that result from this quantum dressing. Perhaps nowhere is the power of QED more evident than in the explanation of the Lamb shift, a small difference in the energy levels of hydrogen atoms that classical physics could not account for. QED reveals that this shift arises from the interactions of the electron with the restless vacuum, a dance of virtual photons that slightly changes the energy of the system. Such subtle corrections, invisible to the eye, are testaments to the power of the quantum field to reshape reality at the smallest scales. The precision of QED comes at a cost. The mathematics of these interactions can lead to infinities, quantities that grow without bound when we try to calculate the effects of the fields at very short distances. To tame these infinities, physicists developed the process of renormalization, a careful balancing act that removes the unphysical infinities and leaves behind finite, meaningful results. This process is not merely a mathematical trick. It is a deep insight into how the quantum world self-regulates, ensuring that the predictions of QED match the reality we observe. In the glow of a computer screen or the beam of a laser, we see the fingerprints of QED in everyday life. The technologies that shape our modern world, lasers, LEDs, the semiconductors that power our devices, are practical manifestations of the principles of QE. They are born from our understanding of how light and matter interact at the quantum level, from the subtle interplay of photons and electrons that QED describes with such clarity. Beyond the laboratory and the devices we use, QED also offers a glimpse into the unity of nature. It shows us that light and matter are not separate, alien to each other, but are bound by the same fundamental laws. Photons and electrons are partners in an endless dance, their interactions governed by the same field equations that describe the gentle bending of a beam of light or the sharp scatter of particles in a detector. This unity is not merely a poetic idea. It is written into the mathematics that QED uses to describe the world. As we contemplate the vastness of the cosmos, it is humbling to realize that this same framework governs the light of distant galaxies and the gentle warmth of a candle flame. The same rules that shape the glow of a neon sign also shape the first light that emerged after the birth of the universe, a faint echo still visible in the cosmic microwave background. QED does not just describe what we see. It connects the smallest scales of nature to the grandest, revealing a continuity that spans the very fabric of the cosmos. And yet, even as QED stands as one of the most successful scientific theories ever developed, it is not the final word. It describes the electromagnetic force with unparalleled precision, but it is only one piece of the larger puzzle of the Standard Model. The strong and weak nuclear forces have their own quantum field theories, each with its own messengers and interactions. Gravity, that most familiar of forces, still resists a quantum description that would fit within this framework. QED, for all its elegance, is a chapter in an ongoing story, a testament to what we have learned and a hint of what still lies beyond. As you drift into sleep, let your mind wander to the quiet hum of these interactions, the invisible exchanges of photons and electrons that shape every corner of the world. In the gentle flicker of a candle, In the silent glow of the stars, Q8 is there, weaving light and matter into a single tapestry. It is a reminder that even in the stillness of night, the universe is alive with quantum whispers, delicate conversations that shape everything we know, and perhaps everything we will ever know. Chapter 4: Virtual Particles, the Hidden Messengers. In the world of quantum field theory, the concept of a particle is more fluid than it first appears. Classical intuition pictures particles as tiny billiard balls, concrete and well-defined. But in the quantum realm, particles are ripples in fields, and even these ripples can take on ghostly, fleeting forms. Virtual particles are the most elusive of these forms. Temporary disturbances that exist only for an instant and vanish just as quickly, yet they are the secret messengers of every force we observe. Virtual particles are not particles in the traditional sense. They do not leave clear tracks in a detector or shine with the glow of a photon's light. Instead, they are internal actors in the stage play of quantum interactions, visible only in the subtle shifts they cause in the energies and trajectories of real particles. They are the conduits through which forces are transmitted, and their existence is woven into the very equations that describe how matter and energy behave at the smallest scales. To understand virtual particles, it helps to step back and consider what it means for something to exist in quantum theory. Real particles, like the electron, the photon, the quark, are excitations of their respective fields that persist in time, carrying energy and momentum in clear, measurable ways. They can be detected, measured, and counted. Virtual particles, by contrast, arise not as independent excitations, but as intermediate states, brief fluctuations that appear in the mathematical description of interactions, helping to mediate the exchange of energy and momentum between real particles. These ephemeral disturbances emerge from the uncertainty at the heart of quantum physics. In the classical world, the conservation of energy and momentum is strict and unwavering. But in the quantum world, the uncertainty principle allows for tiny, momentary violations of these conservation laws, provided they happen quickly enough. Virtual particles exploit this loophole. They appear and disappear in such short timescales that they do not break any fundamental rules, yet they shape the forces that govern how real particles move and interact. Consider two electrons repelling each other, a common scene in the subatomic world. In the language of quantum field theory, this interaction is not a direct push from one to the other, but a series of photon exchanges. These photons are not real in the sense of a beam of light. They are virtual, existing only within the interaction itself. They carry the force of repulsion between the electrons, emerging from the electromagnetic field and disappearing before they can ever be observed. It is through these virtual photons that the electrons know to turn away from each other, their paths guided by the invisible hand of quantum fluctuations. Virtual particles are not limited to the electromagnetic force. In the strong nuclear force, virtual gluons zip back and forth between quarks, confining them within protons and neutrons, and ensuring that these composite particles remain stable. In the weak nuclear force, virtual W and Z bosons mediate processes that allow particles to transform, enabling the nuclear reactions that power stars and the decay of unstable nuclei. In every interaction governed by a quantum field, virtual particles are there, stitching the tapestry of matter together with their unseen threads. What makes virtual particles particularly fascinating is that their effects are real and measurable, even if they themselves cannot be directly seen. In precise measurements of atomic energy levels, the tiny corrections introduced by virtual particles reveal themselves as shifts in spectral lines, deviations from what would be expected if only real particles were involved. The Lamb shift, observed in the hydrogen atom, is one such fingerprint, a tiny energy difference that arises because the electron is constantly interacting with virtual photons from the vacuum around it. Virtual particles also give rise to some of the most intriguing phenomena in quantum physics. One example is vacuum polarization, in which the presence of a charged particle distorts the sea of virtual pairs that flicker in and out of existence, momentarily shielding the particle's electric field. This effect subtly modifies the strength of the electromagnetic force, an adjustment that can be measured in high-precision experiments. It is a vivid demonstration that even the emptiest regions of space are alive with activity, shaped by the restless dance of virtual particles. In the realm of the strong nuclear force, the concept of virtual particles is equally essential. Here, the virtual gluons that bind quarks together do more than just carry force. They interact with each other, creating a dynamic environment that defines the very structure of protons and neutrons. This self-interaction of gluons, a unique feature of the strong force, ensures that quarks remain forever confined, locked within the particles that make up the nuclei of atoms. The interplay of virtual gluons and quarks creates a complex, ever-changing landscape that is still being explored in laboratories and particle colliders around the world. Even in the absence of any matter at all, virtual particles leave their mark. The Casimir effect, a subtle force that pulls metal plates together in a vacuum, arises because the presence of the plates alters the quantum fluctuations of the vacuum. In the space between the plates, certain virtual photons are excluded, creating an imbalance that results in a measurable force. Though no real particles are involved, the effect is a clear sign that virtual particles are an integral part of the quantum world. The mathematics of virtual particles is subtle and complex. They appear in the calculations of quantum field theory as internal lines in the diagrams physicists use to visualize interactions, silent contributors that mediate forces without ever making themselves fully real. In these calculations, their brief existence shapes the probabilities of outcomes, guiding how particles scatter and transform. Though they flicker in and out of the equations as quickly as they flicker in and out of the vacuum, their influence is undeniable. What might seem abstract or esoteric about virtual particles becomes deeply connected to the workings of the world around us. The light from the sun that warms the Earth's surface, the stability of the atoms that make up our bodies, the glow of the stars at night, all of these depend on the interactions mediated by virtual particles. They are the unseen architects of reality, shaping everything from the smallest scale of subatomic particles to the grand structures of galaxies. Virtual particles also invite us to think more deeply about the nature of existence itself. In the classical picture, reality is a collection of things, discrete, tangible objects that persist in time. In the quantum field picture, reality is more like a dance of possibilities, with virtual particles appearing as hints of what could be, transient connections that bridge the gaps between what is and what might be. They are not illusions or mere mathematical conveniences. They are the natural expression of the quantum fields that underlie everything. Yet, for all their mystery, virtual particles are consistent with the strict rules of physics. They obey the uncertainty principle and the conservation laws in a way that seems almost paradoxical. They remind us that the quantum world does not conform to our classical intuitions of what it means to be real or unreal. Instead, it offers a broader, richer view of existence, one that includes both the visible and the fleeting, the permanent and the ephemeral. As we contemplate the role of virtual particles in the universe, we are left with a sense of wonder at how much of reality depends on what we cannot see. The world we experience, its solidity, its stability, its dazzling variety, rests on a foundation of interactions that happen beneath the surface, too quick and too subtle for our eyes to catch. It is a world where the boundaries between what exists and what might exist blur, where even the emptiest void is alive with possibility. As you drift into sleep, let the thought of these hidden messengers linger in your mind. They are the quiet intermediaries of nature, weaving together the fabric of the cosmos in a dance that never ends. In their fleeting presence, we find a reminder of the delicate balance that underlies all things, a quiet testament to the power of the invisible to shape the visible, and to the profound mystery at the heart of everything we know. Chapter 5. Renormalization, Making Sense of Infinite Energies. In the early days of quantum field theory, physicists were confronted with a troubling realization. The equations that so elegantly described the dance of fields and particles also predicted infinities, quantities that grew without bound, defying any physical interpretation. These infinities emerged when they attempted to calculate how particles interacted with their own fields or with the fields of other particles. While the equations promised a profound understanding of nature, they also seemed to hint at an underlying inconsistency, a deep flaw that threatened to undermine the entire structure of the theory. Renormalization was born from this crisis. It is a mathematical technique that allows physicists to extract meaningful, finite predictions from the seemingly infinite landscape of quantum field theory. In many ways, renormalization is not just a mathematical fix. It is a profound insight into how the quantum world is structured and how our understanding of reality must be shaped by the scale at which we look. The infinities that appear in quantum field theory arise from the fact that, in principle, interactions can happen at arbitrarily small distances. In the language of fields, this means that the ripples of quantum fluctuations can probe smaller and smaller scales, leading to contributions from all possible energies. When physicists tried to calculate how an electron interacts with the electromagnetic field, they found that the closer they looked, the more intense these interactions became, growing larger and larger until they reached infinity. This situation was more than a mathematical curiosity. It was a profound problem. A theory that predicts infinite values for observable quantities like mass and charge is a theory that cannot describe reality. After all, the mass of an electron is not infinite, and the forces we observe in nature are finite and well-defined. To move forward, physicists had to find a way to make sense of these infinities without throwing away the entire framework of quantum field theory. The key insight of renormalization is that the infinities do not stand alone. They appear in a way that can be consistently subtracted and absorbed into the definitions of the physical quantities we measure. When we observe an electron in an experiment, what we are really measuring is not the bare electron that exists in some abstract, pristine form, but the dressed electron. An electron that is surrounded by a cloud of quantum fluctuations, of virtual particles and fields that modify its properties. In this picture, the mass and charge we measure are not the fundamental parameters of the theory. They are effective quantities that already include the effects of these fluctuations. Renormalization allows us to redefine these physical quantities to include the contributions from all the virtual processes that swirl around them. Instead of focusing on the infinities themselves, we focus on how these measured quantities shift and adjust to absorb the infinities, leaving behind finite, predictive results. This process may sound ad hoc, but it is not. It is grounded in the deep realization that what we measure depends on how we probe the system. In quantum field theory, the behavior of particles and fields depends on the energy scale at which they are examined. Renormalization captures this dependence, systematically accounting for the way quantum fluctuations modify observables as we zoom in or out. It reveals that the infinities are not flaws, but reflections of the fact that the vacuum itself is alive with activity at every scale. One of the most powerful aspects of renormalization is that it preserves the predictive power of quantum field theory. It does not erase the contributions of the high-energy fluctuations. It incorporates them into the definitions of mass, charge, and other fundamental quantities. In doing so, it allows physicists to make calculations that match experimental results to an astonishing degree of accuracy, while acknowledging that these results depend on the scale at which the measurements are made. Renormalization is more than a technical trick. It is a window into the way nature organizes itself across scales. It reveals that the properties of particles are not fixed in some absolute sense. They are shaped and molded by the interplay of quantum fluctuations at every level. The electron's mass, for example, is not simply a fundamental constant. It is an emergent property that arises from the interaction of the electron field with the electromagnetic field, with virtual photons and virtual pairs of particles flickering in and out of existence. This idea of emergence is at the heart of renormalization. The behavior of matter at one scale depends on the cumulative effects of fluctuations at all smaller scales. It is as if the quantum world is a series of nested patterns, each one influencing the next, weaving a complex tapestry that defines what we observe. Renormalization provides the mathematical tools to navigate this tapestry, to see how the patterns fit together without being overwhelmed by the infinities that arise when we look too closely. In the development of quantum electrodynamics, renormalization played a pivotal role. The theory's early triumphs were clouded by the appearance of infinite corrections to the electron's self-energy and magnetic moment. But by applying renormalization, physicists were able to redefine the electron's mass and charge to include these corrections, leading to predictions that matched experiment with unprecedented precision. The success of QED became a powerful demonstration of the validity of renormalization, inspiring confidence in quantum field theory as a whole. Renormalization also laid the groundwork for our understanding of the strong and weak nuclear forces, which operate on scales where the intensity of quantum fluctuations is even more pronounced. In the strong force described by quantum chromodynamics, renormalization reveals that the strength of the force itself depends on the energy scale, an insight that leads to the phenomenon of asymptotic freedom, where quarks behave almost as free particles at high energies. In the weak force, renormalization ensures that calculations remain consistent with the delicate interplay of the massive W and Z bosons that mediate weak interactions. The conceptual shift brought about by renormalization extends beyond the calculations themselves. It forces us to abandon the notion of absolute, unchanging properties for particles. Instead, we must embrace a more dynamic view where what we measure depends on the context of the measurement. Mass, charge, and even the strength of forces become functions of scale, shaped by the quantum fluctuations that permeate the vacuum. This perspective has deep implications for our understanding of the universe. It suggests that the apparent solidity and permanence of matter are illusions born from the interplay of fields and fluctuations. The reality beneath the surface is fluid, shaped by an invisible dance that never stops. Even the constants of nature are not truly constant, but evolve as we peer deeper or step back to see the larger picture. Renormalization also hints at the limitations of our current theories. While it works beautifully for the known forces of nature, it raises questions about how to incorporate gravity, a force that also shapes the structure of the universe, but resists the same mathematical treatment. The search for a quantum theory of gravity is, in many ways, a search for a new kind of renormalization, a way to tame the infinities that appear when we try to quantize the geometry of space-time itself. In the laboratory, the principles of renormalization are not just theoretical. They guide how physicists design experiments and interpret data, shaping the way we probe the smallest scales of matter. The success of the Standard Model, The theory that describes the known particles and forces rests on the ability to apply renormalization and extract precise predictions from a complex web of interactions. Yet for all its technical power, renormalization also carries a quiet, almost poetic resonance. It tells us that the infinities we find in our theories are not failures, but signs of something deeper, an indication that the world is richer and more subtle than we once imagined. It teaches us to look beyond the raw numbers to see the patterns and connections that emerge when we embrace the complexity of the quantum world. As you let these thoughts settle into your mind, consider this: that the very stability of matter, the constancy of the world around us, depends on the subtle balancing act of renormalization. In the quiet hum of the night, in the faint glow of distant stars, these hidden processes continue, weaving the fabric of the universe from the smallest scales outward. Though we may never see the virtual particles or the infinities they bring, we live in a world shaped by their dance, a world where even the impossible is reconciled through the gentle art of renormalization. Chapter 6. Quantum Chromodynamics, the colors of the strong force. In the world of quantum field theory, one force stands out for its astonishing power and mystery. This is the strong nuclear force, the fundamental interaction that binds quarks together to form protons and neutrons, and by extension, the atomic nuclei that make up the matter around us. Quantum chromodynamics, or QCD, is the quantum field theory that describes this force, a theory as elegant as it is formidable, and one that reveals a hidden realm of color charges and ever-present gluons. The term chromodynamics might evoke images of color in the everyday sense, but in QCD, color is a property of quarks and gluons that has no direct counterpart in the visible world. It is a metaphor borrowed to describe an entirely new kind of charge, distinct from the electric charge that governs the interactions of electrons and photons. Where electric charge can be positive or negative, color charge in QCD comes in three types, commonly labeled red, green, and blue, though these labels have no connection to actual color. This notion of color charge is central to understanding how the strong force operates. Quarks, the fundamental constituents of protons and neutrons, carry these color charges. Unlike electrons, which can exist freely, quarks are never found alone in nature. They are always confined within larger particles, bound so tightly by the strong force that tearing them apart is all but impossible under ordinary conditions. Gluons, the carriers of the strong force, are themselves more than mere messengers. In contrast to the photon of quantum electrodynamics, which is electrically neutral, gluons also carry color charge. This property allows them to interact not only with quarks, but also with each other, weaving a complex and dynamic web that traps quarks inside protons and neutrons. This self-interaction is what makes the strong force unique among the fundamental interactions. It grows stronger as quarks are pulled apart, unlike other forces that weaken with distance. To see how this works, imagine the field lines that connect quarks inside a proton. As the quarks move slightly apart, the field lines between them do not thin out and fade as they do with the electric field. Instead, they bundle together, forming narrow tubes of intense energy that resist being stretched. This phenomenon is known as confinement, and it is one of the defining features of QCD. It ensures that quarks remain bound together, never to be seen in isolation. This picture of the strong force as color-charged strings has profound implications. In high-energy collisions, such as those in particle accelerators, the energy stored in these strings can become so great that it snaps. But instead of freeing a single quark, the energy is converted into new quark-antiquark pairs, maintaining the rule that quarks are always confined in color-neutral combinations. It is a vivid demonstration of how the strong force shapes not just the structure of matter, but the very possibility of creating new particles. The gluons that mediate the strong force are themselves carriers of color charge, and this leads to a rich and dynamic environment within every proton and neutron. Gluons are constantly exchanged between quarks, creating a sea of interactions that define the properties of these particles. But because gluons interact with each other, this sea is not a simple background. It is a roiling, ever-changing medium, a storm of color fields that makes the strong force so powerful and so difficult to calculate. In this environment, the quarks themselves are never static. They are constantly in motion, exchanging gluons and shifting in response to the dynamic fields that surround them. Even the idea of a proton as a collection of three quarks, a picture that served us well for many decades, is incomplete. Modern understanding, guided by QCD, shows that the proton is more like a seething cloud of quarks and gluons, with the three primary quarks joined by a sea of virtual quark-antiquark pairs and gluons that flicker in and out of existence. This dynamic view of the proton and neutron reshapes our understanding of matter itself. It shows that the mass of these particles does not come simply from the masses of the quarks they contain. Instead, much of the mass arises from the energy stored in the gluon fields and the restless dance of quark-antiquark pairs within the nucleon. This insight reveals a profound truth, that the mass of the visible universe, of the stars, the planets, and even our own bodies, comes not from the bare mass of quarks, but from the energy of the strong interactions that bind them together. One of the most fascinating features of QCD is the phenomenon known as asymptotic freedom. Unlike the electromagnetic and gravitational forces, which grow stronger as particles come closer, the strong force becomes weaker at very short distances. As quarks approach each other at high energies, they begin to behave as if they are nearly free, a surprising reversal of the confining force that binds them so tightly at larger distances. This behavior was a breakthrough discovery, revealing that the strong force has a dual nature, confining at everyday scales, but gentle at the heart of high-energy interactions. Asymptotic freedom has been confirmed in experiments that probe deep inside protons and neutrons, such as those conducted at high-energy particle colliders. It is a striking demonstration of how the behavior of the strong force depends on the scale of observation, and it underscores the importance of the energy landscape in determining the interactions of quarks and gluons. At short distances, the quarks appear to move as if they are free, while at larger distances, the confining strength of the strong force asserts itself once again. The complexity of QCD, with its self-interacting gluons and color charges, makes it one of the most challenging theories in modern physics. Unlike quantum electrodynamics, where precise predictions can be made with relative ease, QCD requires sophisticated mathematical techniques and powerful computational tools. Lattice QCD, a method that simulates the behavior of quarks and gluons on a discrete grid of space and time, has become an essential tool for exploring the rich dynamics of the strong force. These numerical experiments offer insights into the properties of hadrons and the phase transitions that occur in the hot, dense matter created in high-energy collisions. The role of QCD extends far beyond the atomic nucleus. In the extreme conditions of the early universe, just moments after the Big Bang, matter existed in a state known as the quark-gluon plasma. In this state, the usual confinement of quarks and gluons was temporarily lifted, creating a fluid of free quarks and gluons that flowed with nearly perfect fluidity. Modern experiments, such as those at the Large Hadron Collider, have recreated this primordial state in miniature, offering glimpses into the earliest moments of the cosmos and the behavior of QCD under extreme conditions. The study of QCD is not just an academic exercise. It is essential for understanding the stability of matter and the forces that govern the universe. It tells us why protons do not fall apart, why the nuclei of atoms are stable, and why the world as we know it can exist at all. It explains why the sun shines, converting the energy of quark interactions into the light and warmth that sustain life. It connects the smallest scales of nature to the largest, revealing a thread of continuity that runs through all of existence. Yet, for all its explanatory power, QCD also challenges our understanding. Its equations are subtle and nonlinear, defying simple solutions and demanding deep mathematical insight. The world of color charges and self-interacting fields is one of constant change, where the boundaries between what is real and what is virtual blur in the quantum haze. It is a realm where the familiar rules of force and motion give way to a deeper logic, one that we are still learning to fully comprehend. As you imagine the world at the smallest scales, let yourself be carried by the idea that every proton in your body is a tiny storm of color and motion. That even in the quiet of a sleeping world, the quarks and gluons within you are ceaselessly at play, bound by the strongest force known to nature. In this invisible theater of color charge, the universe finds its most intimate expression. And we find a reminder that we too are woven from the threads of the quantum world. Chapter 7. The Gluon Sea, What Holds Quarks Together. At the very heart of the visible universe lies a world so small and dynamic that it challenges our most basic ideas of what matter is. This is the world of quarks and gluons, a realm governed by the strong nuclear force and the intricate language of quantum chromodynamics, QCD. Here, matter is not a collection of static particles, but a seething ocean of interactions and exchanges, a perpetual dance of fields that creates the stability and structure of the protons and neutrons that build the world around us. While quarks are often described as the fundamental constituents of protons and neutrons, they are not the only players in this microcosmic drama. Gluons, the carriers of the strong force, are equally essential. Unlike photons in the electromagnetic field, which merely passively mediate forces between charged particles, gluons are far more participatory. They do not simply flit between quarks as intermediaries. They themselves carry the color charge that defines the strong interaction, making them active participants in the stormy interior of hadrons. This difference creates a unique environment inside protons and neutrons. Rather than a few quarks sitting quietly in a confined space, these particles are home to a churning, ever-changing sea of gluons that continuously exchange energy and momentum. The interactions of these gluons with quarks and with each other generate a dynamic landscape that is as complex as it is beautiful. The concept of the gluon sea arises from the realization that the strong force is not a simple static field. Instead, it is a restless environment where gluons are constantly being created and annihilated, their presence ephemeral yet profoundly influential. Unlike electric charge, which is carried only by matter particles like electrons and protons, color charge can be carried by gluons themselves. This self-interaction leads to a rich structure in which gluons do not just mediate forces but also shape the very nature of the force field. Inside a proton, for example, gluons are continually emitted and reabsorbed by quarks. But because gluons can interact with each other directly, the result is not a tidy exchange of force carriers, but a chaotic and energetic dance. The gluon sea is a dense cloud of interactions that stabilizes the proton and gives it its unique properties. In this ever-changing environment, quarks are not frozen in place. They move and shift in response to the pressures and pulls of the gluon fields that surround them. This picture of a proton as a swirling cloud of quarks and gluons is far removed from the simple idea of three static quarks. The quarks themselves are embedded in this gluon sea, and the boundaries between what is quark and what is gluon blur in the depths of the quantum field. In fact, modern experiments have shown that much of the mass and momentum of a proton comes not from the three quarks alone, but from the collective energy of the gluon fields and the interactions that bubble within. These insights into the structure of the proton have been made possible by deep inelastic scattering experiments, in which electrons are fired at protons with enough energy to probe their inner workings. These experiments reveal that the proton's momentum is shared not only by the quarks, but also by a vast number of gluons and transient quark-antiquark pairs. The proton, it turns out, is a dynamic, living system, an ocean of quantum activity where the gluon sea plays a starring role. The gluon sea is more than just a collection of transient particles. It is a fundamental feature of how the strong force operates. Because gluons carry color charge, they create a feedback loop. As they move and interact, they generate more color fields, which in turn produce more gluons. This self-sustaining environment makes the strong force incredibly powerful and ensures that quarks remain bound together in a tight embrace. One of the most intriguing aspects of this gluon sea is how it contributes to the stability of protons and neutrons. The confining nature of the strong force, which traps quarks inside hadrons, is a direct result of the self-interacting behavior of gluons. As quarks attempt to move apart, the gluon fields grow more intense, pulling them back together with an unyielding strength. This dynamic equilibrium is not just a balance of forces, but a constant negotiation within the gluon sea, a negotiation that defines the very existence of matter. In high-energy environments, such as those created in particle colliders, the gluon sea becomes even more apparent. When protons collide at near-light speeds, the intense energy can liberate some of the gluons and quarks from their usual confinement, creating a brief state known as the quark-gluon plasma. In this state, the distinctions between individual protons and neutrons blur, and the sea of gluons becomes a nearly perfect fluid, a glimpse into the earliest moments of the universe when matter itself was unbound. The study of this plasma provides insights into how the gluon sea behaves under extreme conditions, offering a window into the universe's earliest epochs. It shows that the properties of the gluon sea are not static. They shift and evolve depending on the energy and environment, adapting to the circumstances in ways that classical physics cannot fully capture. These discoveries also deepen our appreciation for the strength and subtlety of the strong force, how it can hold quarks in place with ferocious intensity, yet also flow like a liquid when the conditions are right. The richness of the gluon sea has profound implications for our understanding of mass. While we often think of mass as an intrinsic property of particles, much of the mass of protons and neutrons arises from the energy stored in this sea. The quarks themselves account for only a small fraction of the total mass. The rest comes from the relentless activity of the gluon fields and the kinetic energy of the quarks as they dance within this quantum ocean. This realization transforms our picture of mass from a static, intrinsic quantity to an emergent property of a dynamic system. Gluons themselves are massless, yet their interactions are responsible for giving mass to the particles that make up the nuclei of atoms. It is a subtle but profound truth that the mass of the visible universe owes much to the invisible gluon sea. In this way, the humble gluon, an elusive, ephemeral carrier of the strong force, plays a central role in the story of existence, anchoring the solidity of matter in an ocean of motion. Even today, the full complexity of the gluon sea is not fully understood. Physicists continue to refine their models and conduct experiments to uncover its mysteries. The self-interaction of gluons makes the calculations of QCD challenging, requiring powerful computers and innovative mathematical techniques to simulate the behavior of these fields. Each step forward in this exploration brings new insights into the nature of matter and the profound unity of the quantum world. As you reflect on this hidden realm, consider the quiet miracle of the gluon sea. In the tiniest spaces within every atom, there is a churning ocean of energy and motion, an endless exchange of invisible messengers that hold the universe together. The stability of the world around us, the solidity of a rock, the warmth of a sunbeam, the beat of a heart, rests on this ceaseless dance of color and force. As you drift into sleep, let your thoughts wander to that ocean within. The Gluon sea, though forever out of sight, is always present, shaping the universe in ways we are only beginning to grasp. In its constant motion and hidden depths, it reminds us that the world we see is only part of a larger story, a story of dynamic fields and ephemeral particles, of forces that bind and shape reality itself. And in that story, even the quietest moment is alive with the restless murmur of the quantum sea. Chapter 8: Asymptotic Freedom, When Forces Weaken at Small Scales. Among the many revelations of quantum field theory, few are as surprising or as counterintuitive as the phenomenon known as asymptotic freedom. In our everyday experience, forces diminish as objects move farther apart, like the weakening pull of gravity when we leave the Earth's surface. We expect, almost instinctively, that the closer two objects are, the stronger the force between them becomes. But within the heart of the strong nuclear force, nature has written a different script. One where the strength of the interaction actually fades as the quarks that carry color charge draw closer together. Asymptotic freedom was not anticipated in the early development of quantum chromodynamics. For years, the prevailing wisdom was that the strong force, responsible for binding quarks inside protons and neutrons, would behave like the familiar forces of gravity and electromagnetism. Yet, experiments probing the structure of protons and neutrons at very high energies began to suggest otherwise. When physicists scattered electrons off protons with greater and greater energy, they discovered that the quarks inside seemed to behave more like free particles than bound ones. It was as if the fierce grip of the strong force loosened at small distances, contradicting classical expectations and opening a window into the hidden dynamics of the quantum world. To understand this surprising behavior, it helps to step back and consider what happens when we explore the inner structure of a proton. The deeper we probe, using high-energy collisions to investigate smaller and smaller distances, the more we encounter the true nature of the strong force. At larger distances, the force is so powerful that it confines quarks, preventing them from escaping the proton or neutron. But as we push to smaller scales, the mathematical structure of quantum chromodynamics reveals that the strong force does not simply remain constant or grow stronger. Instead, it fades, allowing quarks to move as if they were almost free. This counterintuitive behavior arises from the unique properties of the strong force's carriers, the gluons. Unlike the photon of electromagnetism, which is electrically neutral, gluons themselves carry color charge. This means they can interact with each other directly, creating a dense and complex environment of gluon self-interactions. These interactions modify how the force behaves depending on the energy scale at which it is examined. At small distances, the self-interactions of the gluons lead to a kind of screening effect, where the color charge of a quark becomes partially hidden by the cloud of gluons and quark-antiquark pairs that surround it. This dynamic rearrangement of the vacuum reduces the effective strength of the strong force, a process encoded in the mathematical machinery of quantum chromodynamics. Rather than pulling more strongly as the distance shrinks, the force relents, revealing a hidden softness that belies its usual reputation for ferocity. This phenomenon is known as asymptotic freedom, a term that captures the paradoxical idea that quarks become increasingly independent of each other as they draw closer together. It is as if, deep inside a proton, the quarks live in a temporary state of liberation, only to be recaptured by the strong force as they drift farther apart. This delicate balance between confinement at larger scales and freedom at smaller ones is a hallmark of the strong interaction and one of the defining features of quantum chromodynamics. The discovery of asymptotic freedom was a landmark moment in physics, recognized as one of the great theoretical breakthroughs of the 20th century. It provided an elegant explanation for the experimental observations of deep inelastic scattering, where quarks within protons appeared to behave like free particles when probed at high energies. More than that, it validated quantum chromodynamics as the correct theory of the strong interaction, cementing its place within the standard model of particle physics. Asymptotic freedom also offers a powerful illustration of how the properties of quantum fields are not static, but depend on the scale of observation. In the quantum world, what we measure is never entirely independent of how we choose to measure it. The strength of the strong force is not a single fixed value, but a running quantity that changes with energy and distance. This running of the coupling constant, as it is called, reflects the deep interplay between particles and the vacuum, where virtual gluons and quark-antiquark pairs continuously reshape the fields that govern matter. At high energies and small distances, the quarks within protons and neutrons become nearly free, behaving almost as if the strong force were not there at all. This freedom does not last long. At larger distances, the force returns with overwhelming strength, ensuring that quarks remain confined within the composite particles of the atomic nucleus. This dual nature of the strong interaction, fierce at large scales and gentle at small ones, is a testament to the richness and subtlety of the quantum world. The existence of asymptotic freedom has profound implications for how we understand the early universe and the formation of matter. In the searing heat of the first microseconds after the Big Bang, the universe was filled with a quark-gluon plasma, a state where quarks and gluons moved freely in a hot, dense fluid. In this state, the usual confinement of quarks was lifted, and the strong force's usual stranglehold was temporarily undone. As the universe expanded and cooled, asymptotic freedom receded, and the quarks and gluons once again became locked inside protons and neutrons, giving rise to the building blocks of atoms. This story, written into the structure of matter, is a reminder of how the world we experience today emerged from a much simpler and more chaotic state. The quarks and gluons that were once liberated now find themselves bound by the very force that once allowed them to move so freely. It is a subtle interplay that shapes the composition of the universe, connecting the smallest scales of matter to the largest structures of galaxies and stars. In modern experiments, asymptotic freedom allows physicists to use powerful mathematical tools known as perturbative calculations to make predictions about high-energy processes. At these small scales, where the strong force is weaker, the complex equations of quantum chromodynamics become more tractable, enabling precise tests of the theory. These tests, carried out in particle accelerators around the world, confirm again and again that the universe follows the delicate logic of asymptotic freedom. But for all its successes, asymptotic freedom also hints at the limitations of our understanding. It reminds us that the forces of nature are not simple or static. They are dynamic, their strength and behavior evolving with the scale at which they are probed. The strong force, so overwhelming at the scale of atomic nuclei, yields to a hidden softness at the smallest distances, revealing a world that is at once unified and fragmented, simple and complex. This perspective challenges our classical intuitions about force and matter, suggesting that what we see is only one layer of a much deeper reality. The quiet interplay of gluons and quarks, the running of the coupling constants, and the dance of asymptotic freedom all point to a universe that is more intricate and interconnected than it appears on the surface. As you let these thoughts settle in your mind, consider that within every atom, the quarks that make up protons and neutrons live in a world of constant negotiation, a balance between the freedom they find at short distances and the confinement that binds them together at larger scales. In the quiet darkness of night, as the universe stretches out above you. Remember that deep inside the smallest particles, there's a hidden freedom that emerges only when the distances shrink and the energies grow. It is a gentle reminder that even the most powerful forces can yield to unexpected grace, and that the universe is always more subtle and more beautiful than we can imagine. Chapter 9. Quantum Fields in the Vacuum, Zero-Point Energy's Role. In the classical worldview, a vacuum is the ultimate expression of emptiness, an expanse devoid of matter, light, or energy, a void so absolute that nothing could disturb its stillness. It is a backdrop to the drama of the universe, an infinite stage upon which the actors of matter and light perform their roles. Yet quantum field theory reveals a truth that is far richer and far stranger. The vacuum is not empty at all. It is a dynamic, ever-shifting sea of activity, alive with the restless energy of quantum fields. This hidden activity is known as zero-point energy, and it arises from the very foundations of quantum theory. Even when a quantum field is in its lowest possible energy state, it cannot be truly still. The uncertainty principle ensures that fluctuations, tiny tremors of the field, persist even in the absence of any particles. These fluctuations are the unavoidable background noise of the quantum world, a whisper of motion that cannot be silenced. Every quantum field, the electromagnetic field, the quark and gluon fields of the strong interaction, and others, has its own zero-point energy. It is the gentle murmur of these fields that fills the vacuum, creating a subtle energy density that pervades every corner of space. These fluctuations are not visible to the naked eye, nor can they be detected directly like a flash of light or the path of a charged particle. But their effects are real and measurable, shaping the behavior of matter in profound and unexpected ways. One of the most striking consequences of zero-point energy is seen in the phenomenon known as the Casimir effect. When two uncharged parallel metal plates are brought very close together in a vacuum, they experience a gentle attraction toward each other. This force is not due to any conventional charge or field in the usual sense. It emerges because the presence of the plates alters the quantum fluctuations of the electromagnetic field between them. In the narrow gap, certain modes of vibration are suppressed, creating a slight imbalance in the zero-point energy that pulls the plates together. It is a subtle but tangible demonstration that the vacuum is not empty, but filled with the ceaseless flicker of quantum fields. Zero-point energy also plays a role in the stability of atoms themselves. In the hydrogen atom, for example, the electron's motion is governed not only by the electric field of the proton, but also by the zero-point fluctuations of the electromagnetic field. These fluctuations shift the energy levels of the atom ever so slightly, an effect known as the Lamb shift. Though tiny, this shift has been measured with extraordinary precision, offering yet another window into the restless energy of the quantum vacuum. Beyond these specific effects, the concept of zero-point energy challenges our very understanding of what it means for something to exist. In the quantum field picture, there is no absolute stillness, no perfect silence. Even in the absence of matter and light, the vacuum is alive with possibility, a stage that is never entirely empty, always ready to give birth to new excitations if given the slightest push. The fields that fill the vacuum are not passive. They are active participants in the universe's story, constantly fluctuating, constantly contributing to the structure of reality. The existence of zero-point energy has profound implications for the cosmos as a whole. In modern cosmology, it is linked to the concept of dark energy, the mysterious force driving the accelerated expansion of the universe. While the precise relationship between zero-point energy and dark energy remains one of the great puzzles of physics, the idea that the vacuum itself might possess an intrinsic energy that shapes the fate of the cosmos is a humbling and awe-inspiring thought. These insights also force us to reconsider the very definition of energy and matter. In the classical view, energy is associated with motion or the potential for motion, something that must be supplied from outside to set things in motion. But in the quantum view, energy is woven into the very fabric of existence. Even in perfect stillness, energy is present, encoded in the fluctuations of fields that are as real as the particles they give rise to. The idea that the vacuum is not empty but full of activity has practical implications as well. In high-energy physics, the behavior of particles in accelerators and detectors is influenced by the zero-point energy of the surrounding fields. The interactions of virtual particles, ephemeral yet essential, leave imprints on the scattering patterns and decay rates that physicists observe. These imprints are not mere curiosities. They are vital clues to the underlying dynamics of the fields that shape our world. Zero-point energy also underlies some of the most ambitious and speculative ideas in theoretical physics. In the search for a unified theory of all forces, physicists have proposed that the vacuum might be a kind of dynamic medium, a field of fields that determines the properties of space and time themselves. In this view, the fluctuations of the vacuum are not merely background noise. They are the very essence of reality, a living canvas upon which the patterns of the universe are painted. The mathematics of zero-point energy can be daunting, filled with infinities and subtle subtractions that challenge even the most seasoned minds. But at its core lies a simple and profound idea that the vacuum is not a static void, but a dynamic entity that shapes and is shaped by the quantum fields it hosts. It is a reminder that what we think of as empty space is, in fact, a reservoir of potential, a wellspring of energy that underpins the stability and structure of everything we know. In experiments and observations, the fingerprints of zero-point energy are everywhere. If we know where to look, they are in the gentle pull of the Casimir plates, in the slight shifts of atomic energy levels, in the delicate corrections to the forces that bind matter together. They are in the very fact that matter itself exists, held together by the interplay of fields that never rest. As we contemplate the role of zero-point energy in the universe, we are reminded of the delicate balance that underlies existence. The fluctuations of the vacuum are not chaos, they are the quiet murmur of order at the deepest level of nature. They are the invisible threads that bind the fabric of space and time, the ever-present breath of the quantum world. In the quiet of the night, as you close your eyes and drift towards sleep, let yourself imagine this hidden symphony, the endless, gentle quiver of fields that fill even the emptiest corners of the cosmos. In that flicker of energy, in that ceaseless motion, lies the promise of creation and the quiet persistence of reality itself. And though we may never hear its music directly, we live within it always, carried by the whispering tide of quantum fields that shape all that is and all that will be. Chapter 10. The Future of Quantum Field Theory Beyond the Standard Model. Quantum field theory has proven itself as one of the most profound and successful frameworks in the history of science. From its earliest beginnings in the merging of quantum mechanics with special relativity, to its triumphs in describing the electromagnetic, weak, and strong forces, it has provided a language that captures the fundamental interactions of the universe with remarkable precision. The Standard Model, built upon these ideas, stands as a crowning achievement, a theory that unifies quarks, leptons, and gauge bosons into a coherent whole, tested and confirmed by countless experiments over decades. Yet even as we celebrate its success, it is clear that the Standard Model is not the final chapter of nature's story. The Standard Model, for all its elegance and predictive power, leaves many questions unanswered, many mysteries unresolved. It does not include gravity, the force that shapes the large-scale structure of the cosmos. It cannot account for the dark matter that bends the paths of galaxies or the dark energy that drives the expansion of the universe. It does not explain why the fundamental particles have the masses they do, or why the forces of nature have the strengths that they exhibit. And so, the future of quantum field theory lies in the search for something more, a deeper framework that can reach beyond these limitations and reveal the fuller tapestry of reality. One avenue in this search is the effort to extend the standard model by incorporating new symmetries and particles. Supersymmetry, or SUSY, is a prime example. It posits that every known particle has a partner with different spin properties, a superpartner that could help stabilize the quantum corrections to the Higgs field, addressing the so-called hierarchy problem. These superpartners could also provide candidates for dark matter, particles that interact only weakly with ordinary matter and light. While supersymmetric particles have yet to be observed in experiments like those at the Large Hadron Collider, the search continues, driven by the promise of a deeper symmetry that might unify matter and forces more completely. Another promising path lies in the exploration of grand unified theories, or GUTs. These theories propose that at incredibly high energies, the electromagnetic, weak, and strong forces merge into a single, more fundamental force. The idea of unification has a deep and compelling logic, echoing the way that electricity and magnetism were shown to be two aspects of the same interaction in the 19th century. GUTs predict that the differences we observe in the strengths of forces today arise from the breaking of this unified force as the universe cooled after the Big Bang. While experimental confirmation of grand unification remains elusive, the theoretical allure of such symmetry continues to inspire new models and new insights. Yet perhaps the most profound challenge to quantum field theory is the task of incorporating gravity. General relativity, our best theory of gravity, describes the bending of space-time by mass and energy, a geometric vision that has passed every experimental test to date. But general relativity is a classical theory, not a quantum one. When physicists try to quantize gravity in the same way as other fields, they encounter infinities that cannot be renormalized, a breakdown that suggests the need for a radically new approach. The quantum and the geometric seem to resist a simple merger, hinting that our understanding of space-time itself might need to evolve. One approach to this challenge is string theory, which suggests that the fundamental entities of nature are not point-like particles, but tiny, vibrating strings. In this framework, the different particles we observe are simply different vibrational modes of these strings, and gravity emerges naturally as one of the modes of vibration. String theory also brings with it the possibility of extra dimensions beyond the familiar three of space and one of time, opening up a rich and complex landscape that might contain the seeds of a truly unified theory. Although still speculative and lacking direct experimental evidence, string theory has driven a deeper understanding of quantum fields and has revealed surprising connections between seemingly unrelated areas of physics. Another perspective comes from loop quantum gravity, an approach that seeks to quantize space-time itself, treating space and time as woven from tiny loops of quantum geometry. This theory suggests that space-time is not continuous, but has a granular structure at the smallest scales, a profound departure from the smooth geometry of general relativity. While loop quantum gravity has yet to yield the same sweeping unifications as string theory, it represents another avenue in the search for a quantum theory of gravity, a testament to the creativity and diversity of ideas in modern physics. The search for a deeper theory is not just about extending the standard model or quantizing gravity. It is also about understanding the foundations of quantum field theory itself. The very idea of a quantum field, a continuous entity that vibrates and fluctuates everywhere in space and time, invites questions about the nature of reality. Are fields fundamental, or might they emerge from something even more basic, such as information or quantum entanglement? Some researchers have proposed that space-time itself might be an emergent phenomenon, arising from patterns of entanglement in a more abstract quantum substrate. This idea challenges our most basic intuitions and suggests that the future of quantum field theory may lie not in refining the fields we know, but in uncovering the deeper principles from which fields themselves emerge. In parallel with these grand theories, the tools of quantum field theory continue to evolve and find new applications. Techniques developed to understand high-energy collisions are now used to explore the behavior of exotic states of matter, such as superconductors and superfluids. The mathematical structures of quantum fields have found echoes in the study of topology and geometry, bridging gaps between physics and pure mathematics. Quantum field theory has even found surprising applications in the study of information, inspiring new ways to think about quantum computation and cryptography. These developments show that quantum field theory is not a static edifice, but a living framework capable of adaptation and growth in unexpected directions. Experiments, too, continue to push the boundaries of our understanding. The discovery of the Higgs boson confirmed a key element of the Standard Model, but it also raised new questions about the nature of the vacuum and the stability of the universe itself. Observations of neutrino oscillations have revealed that neutrinos have mass, a fact not accounted for in the original Standard Model, and a clue that there is more to discover. Searches for dark matter and dark energy probe the limits of our theories, hinting at new fields or particles that might lie beyond our current reach. These experiments are not just about filling in the gaps of an incomplete picture. They are about testing the very foundations of quantum field theory, probing its limits, and seeking the signs that point the way to what comes next. In this spirit, physicists pursue precision measurements of rare processes, collisions at ever higher energies, and observations of the cosmos that might reveal subtle fingerprints of new physics. Each experiment is a dialogue with the universe, a question posed in the language of quantum fields and answered in the quiet traces of data. As we look to the future, it is clear that quantum field theory will remain a central pillar of our understanding of nature. Its language of fields and fluctuations, its deep symmetry principles and renormalization techniques have proven themselves again and again. But it is also clear that the story is not finished. The mysteries of dark matter, the enigma of dark energy, the puzzle of quantum gravity, all these call for a new synthesis, a framework that can encompass the known and the unknown in a deeper unity. In this quest, there is a sense of both humility and wonder. Humility because the more we learn, the more we realize how much remains hidden. Wonder because each new insight reveals a universe more subtle, more interconnected, and more alive with possibility than we could have imagined. Quantum field theory, born from the union of quantum mechanics and relativity, has given us a glimpse of the underlying order of the cosmos. What lies beyond that glimpse is a mystery that invites us to keep asking, keep exploring, and keep listening to the quiet murmur of the quantum fields. As you let these thoughts settle and your mind drifts toward rest, consider that the search for the next layer of reality is not just a scientific journey. It is also a human one. It is driven by the same curiosity and wonder that have always carried us forward, from the first sparks of fire to the quiet glow of distant galaxies. In the interplay of fields and forces, in the search for a deeper unity, we find not just the answers to equations, but the reflection of our own place in the cosmos. And in that reflection, we glimpse the possibility that the universe is not only comprehensible, but also profoundly and beautifully alive. Thank you for joining me on this journey through the quantum realm. As you drift deeper into sleep, remember that even in the quiet of night, the universe is alive with the soft whispers of fields and forces. If you're still awake, I invite you to explore another video in this series, where the mysteries of the cosmos continue to unfold, one gentle ripple at a time. Sleep well and sweet dreams among the stars.